Hello everyone, and today I'm going to talk about the science behind Shinkansen. There's a brief history. So the Shinkansen was first entered service in October 1964. It's got the top speed of around 210 kilometers an hour at a time. Initially, it was built to connect Japanese cities, more specifically Osaka and Tokyo. After just 3 years of service, it served more than 100 million passengers. And since 1964, it moved over 10 billion people without a single casualty. Its average delays measured in just seconds. And these are some of the models. You can see here, obviously, the first, the top left is the original one, the first ever Shinkansen, and you can see the design. It progresses quite noticeably. So the evolution of the nose, well, the model at the right and the left here is not actually the Shinkansen, but I think it's just a good-looking model. Makes the presentation a bit cooler. So when all the Shinkansen trains rush into a narrow tunnel at high speed, this created a problem because the air in the narrow tunnel couldn't quite exit through the back of the train, on the top of the train, or the bottom of the train. So the only way the compressed air can exit is through a tunnel exit. So it created a loud booming noise that can be heard for 400 meters away. The guy who solved this problem was Eiji Nakatsu. So he was the general manager of the technical development department in Japan. He was a bird watcher as well. So he took the design of the kingfisher beak, and he designed the nose of the train after the beak. Because the beak is much more pointier than normal, like general bird's beak. As the kingfishers entered water, there's less force exerted on the beak because of the less surface area. Therefore, the kinetic energy of the kingfisher's beak is lost more slowly, and that's why it enables the kingfisher to catch a prey at high speed, so the prey cannot escape. A little bit more on the air resistance. So there are two types of drag force. The first one being initial drag force. It depends on the drag coefficients, also the surface area of the object, the cross-sectional area, and it also depends on the fluid's density rho, and also the speed of the object squared. So suppose air with density rho moving at speed u meets a solid flat surface with area A and loses all of its forward momentum. In a time interval t, the value v of air deflected is just ut times a. You can see there that volume is just distance times area there. So that's it. That's the value. But we also know that the mass is just rho v, so that's just rho aut, and also the momentum, that's mass times velocity, so that's rho a u squared t. But we also know that force is just the rate of change of momentum, so that's just rho a u squared, which is quite similar to the inertial drag force formula there. And this picture here shows drag coefficients of various types of G. you can see there that the streamlined body has got a very low drag coefficient of 0.04. The next is viscous drag. It involves forces between layers of fluids as they flow around an object. If you have a sphere, the viscous drag on a sphere is just 6 pi times the sphere's radius times the viscosity eta times the velocity of the sphere. If you look at picture number 3 here, you can see that there's a laminar flow of air as it hits the sphere here. It creates turbulence, which confuses the air, and also it's the kinetic energy of the air is lost. And if you have a look at this graph here, you can see that at higher speed, inertial drag is much more significant than the viscous drag. That is because the inertial drag depends on the velocity squared of an object, but the viscous drag just depends on the velocity. So that's the reason, one of the reason why the Shinkansen nose has to be a streamliner as much as it can be. So let's have a look at the track. The train actually runs on a 1.435 meters wide standard gauge, which is also dedicated just for the train. Banking is also necessary to accommodate train while economy at high speed. Tracks are welded together to make a continuous track. It also helps with the stability of the train, and rail crossing of cars are eliminated. Cars are routed either above or below the track to ensure safe and reliable service. As you can see here, the conventional tracks and carriage are only suitable for low-speed transportation. But the Japanese developed the bank track so that the resultant force that arises from the centrifugal force and the gravity is acted vertically downwards to the car floor as much as possible. Also here, the British already have loads of rail system network anyway, so it is more economically viable for the British to just build a tilting train rather than a whole new track. So let's have a look at the simplified calculation for bank angles. So let's suppose we have a Shinkansen front car of mass 30 tons. It is cornering at a speed of 210 kilometers an hour. The radius of the circular path is 1,800 meters. By modeling the car as a particle and ignoring force from friction and air resistance, find the bank angle of the track. Now we know that there's weight acting on a train and also the resultant force acting at an angle. We can resolve the resultant force to be r sine theta and r cos theta. R cos theta is just mj, and r sine theta is just mv squared over r. That's the centripetal force. Therefore we have tan theta equals v squared over rg. Plugging in the values, we got theta to be 10.9 degrees. Well, I couldn't find the actual value of the bank angles for the Shinkansen, but the TGV, which goes at, although it goes at even higher speed, it's got bank angle of 7 degrees, so it's sort of similar to 10 that we got here, but remember that this is a very rough calculation. We ignore so many variables here. Um, so another problem do arise as technology progress. That allows for an even faster train, but the tracks are already laid and they can't be changed. In other words, the bank angle cannot be changed. So if you want to go cornering and even higher speed, you need a tilting train instead, because that will help minimize the lateral forces. Let's have a look at the superconducting Shinkansen here. Also the SE Maglev. It was first undergone working in 1962. The principle behind that is just propulsion and levitation, really. And the magnetic field generated by the superconducting maglev has no impact on health. At least it was actually regulated and then monitored to keep it below international guidelines. Magnetic shields are also installed on the train and passenger embarkation facilities. The superconducting part of it is just niobium titanium alloy, which is cooled by liquid helium and nitrogen down to negative 296 degrees Celsius. This causes the resistance to become negligible, allowing minimal energy loss when the current is flowing. Repulsion, so a series of north and south magnets are induced due to current flow. This, along with the guideway and magnets switching between north and south and careful timing, allows the train to move forward. You can have a look at the animation here, which is quite self-explanatory. Lastly, the levitation. So the train is levitated using a guideway magnet that has the same polarity as the one on the train to push in another magnet of opposite polarity to pull the train upwards. And that's about it. Thank you very much for watching, and make sure you subscribe to my channel. Thank you very much.